In this video, we'll go over the answer key for Monday, April 20th. And we're going to start by looking at free energy of formation. And the equations and calculation for these problems are more or less the same as the standard energy of enthalpy, where you do products minus reactants and you look up your standard energies of formation from a table. Note that if you're in the pure element, so H2O2, N2, the formation will be 0. So we start with this equation where we have methane going to ethane plus hydrogen gas. And here's our table of delta G's of formation. So to do this, you just do products minus reactants, so C2H6 plus H2 minus 2 moles of CH4, so I need them multiplied by 2. And you should get 69 joules per mole. I believe this is joules, but the answer you should get, if I did my math right, is 69. So delta G, energy, is a state function. What that means is it's very easy to calculate delta G if we know the equations that make up a bigger equation. That is, if you combined equations, you just add delta G's together. Conversely, if you take an equation and just flip it, that is, what were your reactants are now your products, and what were your products are now reactants, all you do is you take your delta G and you flip the sign. Or if you multiply how many moles of a reaction you have, so again, if I have a reaction that has reactants and products, multiply both sides of the equation by 3 moles, all I need to do is take my delta G and multiply it by 3 moles as well. And so we have this problem where I give you an equation and I give you 2 sub-equations, and I want you to figure out what the delta G for this overall equation is. And so this is a big puzzle, really. So let's start with our first equation. So we have iron oxide here as a reactant. This is what we're trying to get to. However, we have iron oxide as a product, so it's on the wrong side of the arrow. So what I did first is I just took this equation and flipped it. And so you have iron oxide going to 2 iron plus 3 half O2. When you flip an equation, you take delta G and change the sign. All right, let's look at the next equation. So my target has 3 CO, and the equation that I gave you only has 1 CO. So what you want to do is multiply this second equation by 3 to get 3 CO, 3 half O2, and 3 CO2. And you take your delta G and you multiply it by 3 as well. Now you can add the 2 equations together. And when you do that, you want to take everything on the left side of the arrow and put that together, and everything on the right side of the arrow, put that together. So you get Fe2O3 plus 3CO plus 3 half O2 goes to 2 iron plus 3 half O2 plus 3 CO2. Notice that you have 3 half O2 on the same side of the, rather different sides of the equation. Here it's a reactant, here it's a product. So what happens is that they get canceled out. They more or less destroy each other. And then for your delta G's, you just want to add your delta G's to get your overall delta G for this reaction, which is minus 29.4 kilojoules. Alright, so let's talk about delta G gives free energy under non-standard reactions. So you have 2 delta G's. You have delta G and delta G naught. So delta G is only equal to delta G naught when the reactants and products are in their standard state. That means their normal state at that temperature. So for example, oxygen should be a gas at 25 C. Carbon should be a solid. The partial pressure of your gases are 1 atmosphere, concentrations 1 molar. So that naught is really meaning standard concentrations. All right. So if you're under non-standard conditions, that is, if any of these are different, you won't use delta G naught, you'll use delta G. And the equation that relates these two together is delta G equals delta G naught plus RT ln of Q. We talked about Q already this semester. It's the reaction quotient. is the concentration of products divided by the concentration of reactants. Let's say you're at equilibrium though. If you're at equilibrium, delta G is 0. That is the definition of delta G. So this will equal 0, and if delta G equals 0, then that must mean that delta G naught equals minus RT ln of Q. And if you remember, we talked about this a month or two ago when we were talking about equilibrium. If you're at equilibrium, you're no longer working with a Q, you're now working with a K. So delta G equals minus RT ln of KEQ. And we'll look at how we use this. Alright, so here's a reaction. First, what is delta G naught at 25C? Well, we can solve this with delta G as a formation like we did in the previous problem. So I give you delta G as a formation. So it's products minus reactants. So CO2 plus 2H2, well, H2 is 0, minus CH3OH. So I have minus a minus, so this is actually plus. So at 25C, delta G naught is 25.1. All right, so let's find delta G now at 25C given these following pressures in the gas constant. So since I'm giving you something outside of standard conditions, we need to use delta G equals delta G naught plus RT ln of Q. So let's start filling in values. Delta G naught, that's what we figured out in A, is 25.1. R, 8.314 times 10 to the minus 3. So you see your delta G naught is in kilojoules. I can't add a joule and a kilojoules together, so what I did is I took our gas constant, divided it by 1,000 to get it into kilojoules. So plus 8.314 times 10 to the minus 3 multiplied by our temperature. So this is in Kelvin, our gas constant, so our temperature needs to be in Kelvin as well, which is 298. Natural log of now we need to put in Q. So remember, Q is the concentration of CO, so products, multiplied by H2 squared, because we have two of them, divided by CH3OH, and then I put in their pressures. When I get that, I see delta G equals 25.1 minus 13.179. Delta G is 11.9 kilojoules per mole. So under these conditions, this reaction is still unfavorable. Remember, delta G that's positive is non-spontaneous, negative spontaneous, 0 at equilibrium. Question 4 is a similar question, so I'll allow you to work on that. Excuse me. Now, this is what I was talking about in the previous slide. Got a little ahead of myself. But if delta G is 0, then delta G naught equals minus RT ln of K. So this tells us the relationship between delta G naught and K. If K is less than 1, that means delta G is positive and the reaction is non-spontaneous. It will go and make reactants. If delta G is greater than 1, or sorry, K is greater than 1, delta G is negative. Reaction is spontaneous. If K is 1, delta G naught is 0. What that means is that our reaction is spontaneous under standard conditions, which is like almost never the case. You're like never going to find a K of 1, but it is possible, or it is plausible rather. So question 5 is again doing everything we did in 3-4. So again, I will leave that to you to figure out how to do it, and I'll post the actual answer key up if you want to follow along. Remember, in standard conditions, our gas is at a pressure of 1. And that is it for this video. So if you still have questions about how to do these calculations, please get at me before next week, because that is when your test is. Alright, I will see you later.